Welcome to The Explainer. Sometimes a simple spreadsheet or table just doesn't cut it, right? It can't really capture all the messy, complex details of the real world. Well, today, we're going to dive into a way of looking at data that thinks less like a rigid table and a lot more like we do by structuring information as a bunch of interconnected, interactive objects.
All right, so here's our game plan. We're going to start by poking some holes in the good old database table. Then, we'll shift gears and start thinking in objects. After that, we'll get into the really cool stuff, the superpowers that make this model tick. We'll see how it's used out in the wild, and then we'll wrap it all up and show you why this is such a big deal.
Okay, first up, the familiar grid of rows and columns. We see it everywhere, from basic spreadsheets to massive databases. It's been the workhorse of data for decades. But, as you're about to see, when things start getting even a little bit complicated, that simple structure, well, it starts to show its age.
So let's make this real. Imagine you're building a database to keep track of cars. Your first instinct, probably, is to make a table. Columns for make, model, year, serial number. It's simple, it's clean, but does that list of facts really describe a car?
Okay, check this out. On the left, you've got the table view. It's static, it's flat, it's just a bunch of facts. But look at the right. The object view isn't just about what a car has, an engine, tires, whatever. It's about what a car can do. It can age, you can replace a tire, you can drive it. And that is the huge leap here. We're packing the data and the behaviors that go with that data all into one neat little bundle.
And that brings us right to the heart of the object-oriented model. It's a totally different way of looking at things. It pushes us to see data not as boring rows, but as digital versions of real-world things.
And this slide right here, this is the fundamental shift. We're not building a library of tables anymore. We're building a living, breathing universe of objects that can interact with each other. You don't just query a table. You can actually talk to a car object and tell it, hey, age yourself by 1 year.
So let's nail this down. An object isn't some generic idea. It is one specific thing. It's not just a car in general. It is your car. It's that specific 2023 Toyota in your driveway with its own mileage, its own history, and this is super important, its own unique identity.
So if an object is the finished product, the class is the factory blueprint. The car class is the master plan. It's the set of rules that says, okay, every single car object we create from this point on is going to have a make, a model, and an engine, and it will know how to do things like age itself.
Now, attributes are pretty straightforward. They're just the specific details about an object. Think of them as the variables. So for one particular car object, the make attribute might be Toyota, and the year attribute might be 2023. Simple as that.
And this is where the real magic is. Methods are the verbs. They're the actions that make the object feel alive. A method like replace tire isn't just a piece of data, it's a capability, a procedure that is literally baked right into the car object itself.
Okay, we've got the basic building blocks down. Now let's get to the fun part, the superpowers that make this model so special. Because it's not just about bundling data and actions. There are two concepts, inheritance and identity, that let us map out the real world in a way that simple tables could only dream of.
All right, inheritance. This is all about being smart and efficient. It's a way to avoid repeating yourself over and over by setting up a kind of family tree for your data. You start broad.
For example, we can create a vehicle class. Think about it. Cars, trucks, motorcycles, they all have an engine, a make, a model, right? So instead of defining those things for every single type, we just define them once, right here in this general vehicle class.
Okay, so now we get more specific. We create a car class, but we tell the system that it inherits from vehicle. This creates what's called an ISA relationship. We're literally saying, hey database, a car is a kind of vehicle.
And this is the brilliant part. The car class automatically gets all that stuff from vehicle, the engine, the make, the model, without us lifting a finger. Then we can add the details that are unique to cars, like bumpers or how many people it can carry. It's just so clean, so logical, and unbelievably efficient.
This is such a classic data headache. In a normal table, if you've got two rows and they look exactly the same name, same age, same town, the database might just think they're duplicates, even if they're two totally different people in the real world.
This quote absolutely nails the problem. A table shows Peter has a kid named John and Susan has a kid named John.
Is that the same John? Or are there two different kids who just happen to have the same name? A traditional database can't tell you. It can see that two rows are equal, but it has no idea if they are the exact same thing.
And here's the beautifully simple solution. The object-oriented model gives every single object a unique, permanent serial number the second it's created. It's called an object identifier, or OID. Think of it like a digital fingerprint for your data. So the two John objects, they'd get different OIDs. Problem solved. It's crystal clear they are two different people, even if every other detail about them is identical.
Okay, this all sounds great in theory, but how do we actually use this stuff? That brings us to the database systems themselves, and there are really two main ways that these object-oriented ideas show up.
This table breaks it down nicely. On one side, you have OODBMS. That's the pure approach. It stores data as objects, it thinks in objects. It's a perfect match for complex apps written in languages like C++. Then you have ORDBMS, the hybrid model. It's like a traditional relational database that's been given some object superpowers. It can give you better performance for simple queries, but it's not a pure object system. The one you choose really depends on what you're building.
So, we've walked through the whole concept, but let's get down to it. Why should you actually care about this? What's the real-world impact of modeling data this way?
Okay, here's the bottom line. This isn't just some abstract theory. The real world is complicated, and our software has to deal with that. This model just lets us build systems that are a much better reflection of that reality. We get cleaner, reusable code because of inheritance, and it solves a massive headache for developers by making the database structure look a lot more like the code they're actually writing. And that kind of leaves us with a final big question to chew on. The whole point of the object-oriented model is to make data reflect the messy, interconnected world we live in. And as our digital lives get even more complex, maybe the question isn't if our databases will need to start thinking more like us, but when.